The next topic after Coulomb's inverse square law is the small topic relative permittivity or dielectric constant. So it's denoted by symbol epsilon r, epsilon r. Now the regular permittivity of a medium is denoted by the symbol epsilon. So this is the permittivity of a medium. Now the permittivity of free space is denoted by symbol epsilon naught. Free space means air or vacuum. Permittivity of a medium means the medium is any general medium. Any liquid or any solid medium it can be considered, but if only vacuum is considered or even air. Now the permittivity of air or vacuum, exactly speaking, it is the permittivity of vacuum. Free space means vacuum, but the consider considering electric forces or electricity, both vacuum and air with respect to electricity or electric charges are found to have same property, just like light waves or light. The behavior of light or the velocity of light both in vacuum and air are found to be almost same. So the difference is neglected, and velocity of light in vacuum means we say that it's velocity of light in vacuum or air. Both of them are one and the same, 3 to 10 power 8 meters per second. The same way with respect to electric charges or the forces between electric charges, it is found that they are identical both in case of vacuum, whether the charges are present in vacuum or whether the charges are present in air also. In both the cases, they are found to be same. That's why permittivity of vacuum means it's also taken as permittivity of free space. So that is permittivity of air also it's taken as. So supposing between the two charges, no vacuum or air is not present, only a material medium, that means a solid medium is present between the two charges, or a liquid medium is present, then in such a case the permittivity is taken as epsilon. That's what we have seen in the Coulomb's inverse square law. Now based on these two permittivities, relative permittivity is defined. It's also called as Directric constant. Now this is a very important topic carrying about 2 marks. So it's only a simple definition. So how it is defined? The permittivity of that is relative permittivity. So it's simply defined like this. So whatever things we are seeing here are simple. Nowhere any complication is there. Just see here. I'm just moving it a little. So the permittivity of a medium is epsilon, and the permittivity of free space is epsilon naught. The ratio of the permittivity of the medium to the permittivity of free space. The ratio means division. So this ratio is simply defined as the relative permittivity of the medium. So already we have seen that permittivity of a medium epsilon depends only upon the nature of the medium along with the temperature of the medium. That means only on the nature of the medium and its temperature, medium's temperature. On that, these two factors only the permittivity actually depends upon. So epsilon naught is what? Permittivity of free space. Free space means empty space, that is vacuum or even air also can be taken. Now this is a constant. So this is always a constant. Always permittivity of free space or vacuum or air is a fixed value. It doesn't change. Experimentally, it has been determined as, already we have seen, 1 by 4 pi into 9 10 power 9 SI units. So already we have seen this in the Coulomb's inverse square law. So this is a constant, almost like a universal constant. Gravitational constant is a universal constant, almost like that. This value is always a fixed constant. So now epsilon r clearly now depends only upon epsilon, but epsilon depends upon what? The nature of the medium and temperature. That means epsilon r also depends upon the nature of the medium and temperature. So that is the simple nature of epsilon r. So it depends only upon epsilon. That means it depends epsilon, which depends only upon the nature of the medium and temperature. So relative permittivity epsilon r also depends only upon the nature of the medium and temperature. So this relative permittivity is also called as dielectric constant. When the word dielectric constant is used, the symbol K is actually used. So this is also called as K. This is also denoted by symbol K. So more clearly, epsilon r or K it is denoted as. So how it is defined? So definition is very simple. It is the ratio of permittivity of the medium to the permittivity of free space. So definition is very simple. So I'm just drawing a box for this. So entirely I'll draw a box. So this is a very important definition. Now from this the units can be obtained from the equation. So once we know the equation for a particular quantity, units can be very easily obtained. So what are the units of epsilon r, or the relative permittivity or dielectric constant? Now epsilon r is actually ratio of two permittivities. So permittivity units already we have seen Coulomb square per Newton meter square. So permittivity of free space also same units. So the unit of relative permittivity is numerator unit divided by denominator unit. Numerator quantity is permittivity of a medium. It is Coulomb square per Newton meter square. So denominator also, it is again a permittivity only. So its units are again the same, Coulomb square per Newton meter square. So both the units will be getting cancelled. So the unit is coming simply as 1. So whenever the unit of any quantity comes as 1, it simply means that it has no units. So for example, coefficient of friction. Coefficient of friction is what? It is a ratio of frictional force. Just see here. So I'm just using a rough column here. So coefficient of friction is denoted by symbol mu. It is the ratio of frictional force to the normal force or normal reaction. So it's ratio of two forces. So force unit is what? Newton. Normal force or normal reaction is also Newton only. So both the units get cancelled. Simply it's coming as 1. So whenever the units of any quantity, so this is equality. Equality means left hand side quantity is same as right hand side quantity. Left hand side quantity is coefficient of friction, right hand side quantity is ratio of the frictional force to the normal reaction. So units means it's denoted by symbol arrow. So instead of putting equality, we have to use the symbol arrow. Arrow always denotes the phrase or words unit of. So unit of mu is what? It's coming as 1. That means it has no units and dimensions. So therefore it has no units. No units means no dimensional formula. So dimensional formula is also a type of unit only. No units means it has no dimensional formula. Whenever a quantity has no dimensional formula, it is said to have no dimensions. So no units and dimensions. So this is a very important property of relative permittivity or dielectric constant. So relative permittivity or dielectric constant has no units and dimensions. Now, so factors, what are the factors? So this also should be mentioned immediately. So what are the factors on which epsilon r depends upon? So epsilon r depends only on the nature of medium and temperature. That means temperature of the medium. These are the factors on which epsilon r depends upon. So definition of relative permittivity is also very simple. So it's the ratio of permittivity of the medium to the permittivity of free space. So now itself, as you are listening to the topic, at the same time you can complete the running notes. Again, need not separate time need not be spent only. So everything else is very clear. So this is sufficient for 2 marks. So the only thing is 2-line definition should be written. This also can be completed now itself. So it is the, so as I am writing, so now itself it's better to take the running notes as you are listening. So again, spending separate time for running notes is unnecessary. I said most important things in science and technology are definitions. So definitions should be by hearted. Always in your notes, definition should be there. If the definition is there, almost everything is there. Because from the definition only we are getting the factors, units, everything for the quantity, relative permittivity or dielectric constant. So strictly speaking, relative permittivity and dielectric constant, they are defined differently. So this is really the definition of relative permittivity only. Dielectric constant definition actually comes a little later. In another topic it actually comes, and from that definition it can be proved that dielectric constant and relative permittivity are one and the same. So presently we are taking them both to be same. Really they are defined differently. So the other definition for dielectric constant actually it comes a little later. So there it becomes more clearer how why k has been defined separately. So now presently we are taking both of them to be same. So it is the ratio of permittivity. So I'm just writing very fast, so at the same time you have to take So don't think that I'll take the notes later. So this is very simple like that. So taking the notes later will not be possible because now itself you are spending some time on listening. Now itself notes should be completed because your notes only will be really helpful. How many, whatever the classes you are listening, all those things only for understanding they'll be useful. Whatever is understood now, if it is not learnt, revised again and again, it will be forgotten. So everything will get wasted. You'll only know that, remember later that it was easy. But what is that? It can't be remembered. So the only thing is always a student or a person related to science and technology. Always he has to be again and again revising the definitions and the laws of a particular lesson, laws or principles. Then only he'll be always ready in touch with the subject. At any moment he can solve any kind of problem. So that's the importance of regular revision or regular practice. So it is a ratio of permittivity. For that reason, your own notes copy is required. So you can't trust soft copy. So I have my notes in the phone. I have the soft copy of notes in the phone or my mail. All that is not sufficient. You should have your hard copy in your own personal notebook, paper notebook. You should be having. It's a ratio of permittivity of a medium to the permittivity of permittivity of, just write the of a little more clearly, permittivity of free space. Free space means air or vacuum. So that is, below that the equation can be written. So that's about the quantity relative permittivity. Now one small thing, very important thing about permittivity of a medium is, so we have seen, now we'll just the permittivity of a medium always is found to be greater than the permittivity of free space. Later the reason exactly will be coming. Already previously roughly we have seen the reason. Roughly, only roughly, we did not see it exactly. Later, little later it will be coming more clearly. So for any medium, so very important thing is, for any medium compared to free space, that means compared to vacuum, exactly speaking vacuum or roughly air or vacuum. For any medium, permittivity of the medium will be always greater than permittivity of free space. So numerator, just observe the equation here. Numerator is always greater than denominator. That means it's something like 4 by 3 or 5 by 4. 4 by 3 is 1.33. 5 by 4 is 1.25. That means it can be seen that whenever numerator is greater than denominator, always the value will be greater than 1, 1.33, 1.25. This is a very, very, very important result. So this means that the relative permittivity for any medium will be greater than 1. The reason is permittivity of the medium will be greater than permittivity of free space. Always this has been found to be true experimentally and also theoretically also. So later the reason will be coming little more clearly. From Coulomb's inverse square law, this has been actually proved. So for any medium, epsilon is greater than epsilon naught. This simply means that relative permittivity, so which is nothing but Directric constant, is always greater than 1. So this is a very, very, very important result. So this is a very, very, very important result. So the relative permittivity always is greater than 1 for any medium, or Directric constant is always greater than 1. So now consider a simple situation. Now a simple situation is like this. Now consider the actual definition of relative permittivity. So relative permittivity epsilon R stands for relative. That's why it's called as regular permittivity of the actual permittivity of the medium is epsilon. It has its own units, already we have seen. Permittivity of free space also has its own units, but relative permittivity epsilon relative, R stands for relative. So it doesn't have any units and dimensions. So but it depends upon the nature of the medium, because epsilon depends upon the nature of the medium. Permittivity epsilon depends on the nature of the medium. Now supposing the relative permittivity of say a wooden block is required, some wooden block which is actually placed between the two charges. always relative permittivity is coming only in the case of force between two charges, where the two charges need medium between the two charges is very important here. So whatever medium that is placed between the two charges q1 q2, so force between two charges q1 q2 already we have seen from Coulomb's inverse square law, directly proportional to the product of the two charges and inversely proportional to square of the distance, but along with that it's also depending upon the medium that is present between the two charges. So if that medium present between the two charges is a wooden block, so then relative permittivity of the wooden block is required here. So we can find out from using this equation. So numerator will be permittivity epsilon of the wooden block divided by permittivity of free space. Supposing it's a glass block, then relative permittivity of glass block is permittivity of the or permittivity epsilon of the glass block divided by permittivity of free space. So compulsorily, when you are listening, compulsorily you have to be observing the cursor. So because I am pointing out the quantity, or in a diagram, I'll be with the help of the cursor only it's possible to point out. So like in a regular classroom with the help of a, that is with the help, it's simple to observe the equation just because the teacher points out the equation directly on the board itself. So it's almost like a direct teaching. So if you're observing the cursor, if you're not observing the cursor, it's not possible to understand. It's like teacher with invisible teacher teaching. So which point he's teaching, which line he's teaching, which part of the diagram he's explaining, it can't be understood. So there won't be any correlation between the voice and the video. So its disadvantages. Now this is observing the cursor is very important. So the permittivity of the glass block divided by permittivity of free space. So relative permittivity of water. Relative permittivity of water is about 80, roughly about 80. It's a very high value. So already we have seen that relative permittivity for any medium is greater than 1. Again, I'll get the cursor compulsory. So for water it's about 80. For wood, roughly maybe around 5 or 10 like that. But always it's greater than 1. So the relative permittivity of any medium is permittivity of that medium by permittivity of free space. So denominator is never changing. Now consider the special case, a very simple case. What is the relative permittivity of air or vacuum? So it's nothing but permittivity of air or vacuum. Denominator is always the same. Again, permittivity of air or vacuum, that is free space. So here, relative permittivity of air or vacuum means numerator and denominator are coming to be same. Epsilon naught, relative permittivity of air or vacuum is permittivity of air or vacuum. Denominator never changes in the relative permittivity. It's again the permittivity of air or vacuum. That is epsilon naught by epsilon is they get cancelled. Simply one it comes. So only in the case of air or vacuum, relative permittivity comes to be 1. This is very, very important. But for any other medium, it comes to be greater than 1. So this is very, very important. So for air or vacuum, only for air or vacuum, the relative permittivity is the permittivity of air or vacuum divided by permittivity of air or vacuum. They just get cancelled. So simply it comes to be 1. So this is very, very, very important. Only for air or vacuum, relative permittivity comes as 1. But for any other medium, it is greater than 1. That means if we take the medium to be again air or vacuum, in that case, epsilon will become equal to epsilon naught if we consider air or vacuum, including air or vacuum. Excluding air or vacuum, it is greater than epsilon naught. So relative permittivity is greater than 1. If we consider air or vacuum, then it will be equal. Relative permittivity will be equal to permittivity of free space. That means permittivity of air or vacuum. Because we are considering air or vacuum. Permittivity is nothing but permittivity of air or vacuum equal to epsilon naught. Relative permittivity will be equal to 1. So the general relation now for any medium, that means including air or vacuum, the general relation is greater than or equal to 1. So this is taken as the final general relation, general inequality relation for the values of relative permittivity. Always it will be greater than or equal to 1. Only in case of air or vacuum it will be equal to 1. So this is, both are very, very, very important. Now why it is greater than 1? Why can't it be less than 1? The reason for this comes from Coulomb's inverse square law. In the another topic it will be coming. In the topic of dielectric constant it will be coming more clearly. So dielectric constant is a separate topic because it has been defined differently, but both come to be equal. That also, proof also comes from the Coulomb's inverse square law only. So powerful is the it's almost, Coulomb's inverse square law is almost like fundamental law in electricity. Based on, so many times I said From Coulomb's inverse law, other derived laws have been obtained. So now just check this. I'm just separating the units of relative permittivity because there is no place here. So it has no units and dimension. Whenever units of any quantity comes as 1, it simply means that it has no units and dimension. This is very, very important. So unit dimensional formula also is nothing but another type of unit. So dimensional formula also comes as 1. That means it has no dimensions. So now electric field. Now this is another simple definition. So but can't be given for marks. So I'm not putting any marks. So relative permittivity separately it can be asked, but always it's asked only for 2 marks, either definition or equation or say or the values. What is the range of values of relative from 1 to infinity? It can take any value, but always greater than 1 it will be. Only for error vacuum it becomes exactly equal to 1. So separately, like small, very short answer questions, it will be useful. Now consider a simple situation. Say a charge. What is meant by an electric field? Now I'm taking a say positive charge. So denoted by symbol Q. Now consider any point, say A, at some distance away from the charge. So this charge around the charge Q, consider any point in the space surrounding the charge Q. Now if you are putting some other charge here, say another positive charge is placed here, say a unit positive charge is placed here, say something like this, a unit positive charge, or any tiny positive charge, even smaller than the unit positive charge, such a tiny charge whose magnitude tends to 0 is simply called as a test charge, a charge which is used for testing, something like that. So when such a positive test charge is placed here at this point, immediately this charge exerts a force on that charge. This happens whenever the test charge, a unit positive charge or any still tinier charge is placed here at any point in the surrounding space. Always the influence of this charge is actually felt on this other charge, not just another charge, even by any other negative charge or even a neutral body also, like a piece of paper. So already we have seen that a piece of paper gets attracted to a charged body, like a rubbed comb. So the influence of this charge is felt on all other objects in the surrounding space. This surrounding space is simply called as an electric field, or an electric field is said to be present in this surrounding space. So that simply gives the meaning of electric field. So what is electric field? It is nothing but the space surrounding a charge or electric charge where its influence is felt on other objects. That space itself is called as electric field, or in that space electric field is said to be present. So that's the simple definition of electric field. So it is the space surrounding a charge. So whenever I am writing on the board, running notes, so it's all the definition itself. So if it's a definition, suppose this is a simple definition. So whenever I'm writing, it's compulsorily you must take it down, because definitions, however simple they are, they can't be ignored. Because every topic, however complicated it is, it's entirely based on definition. If the definitions are by hearted, almost like it's no almost by hearting should be done for the definitions. Derivations problems, they need not be by hearted because they are directly based on definitions are in the hands. Everything in science and technology becomes very simple. Any problem can be solved. So the problem is not based on a formula. It's based on definitions, scientific definitions and derivations. Formula is based on scientific definitions and derivations. Just without understanding a formula is by heart, it will be helpful only in solving a particular problem. But if the problem model is twisted, it will not be helpful. What is helpful is only definitions, scientific definitions and derivations. Definitions, only few definitions will be there in a lesson, maybe 4 or 5. Less than 10 they will be there. But laws, only 2 or 3 laws will be there. In this lesson, main law is, already we have seen one main law. Just like that, another one law, one or one and a half laws will be there. So if they are by hearted, that's sufficient. all the questions become very simple. All the derivations, all problems will become very simple. So it is a space surrounding a charge. So definitions must not be, you must not take the definitions lightly. It is a space surrounding a charge or surrounding an electric charge. It's more accurate. Surrounding an electric charge where its influence is felt on other objects. Other objects means other objects around it. Now, the strength or intensity of electric field. Now, intensity or strength means how strong the electric field is. So, this strength, how strong the electric field is denoted by a symbol E bar. It's called as simply strength of electric field or electric field strength. Or it's also called intensity of electric field, or in short, it's called electric field intensity. The electric field intensity or electric field strength denoted by symbol E bar. Now, how to know where the electric field is strong? So, Coulomb's universal law helps. Now, imagine a unit positive charge placed here, not a positive test charge. It's just positive unit charge. Even positive test charge also is sufficient, but for the definition, it's defined only for unit positive charge only. The test charge, positive test charge should be a unit charge. Now, imagine a unit positive charge here. Supposing it's placed at some distance, say R units. So, distance between the charge, this is the parent charge which is actually producing the electric field. Now we are using a positive test charge, a unit positive test charge placed at the point A. Now supposing this point A is at large distance, R is very high, then we know that from Coulomb's universal law, force, what kind of force exists between this charge and this unit positive charge? Both are positive charges, so it will be definitely a repulsive force. So repulsive force means it's directed away from the parent charge which is producing the electric field here. So whatever things we are seeing here are simple, so nowhere any complication is there. So the force is a vector, so it's denoted by an arrow. So this is a complete force. F is a symbol used to denote this force, or like any regular force. So this force clearly acting on the unit positive charge here. It is repulsive, so it's directed away from this charge. So always force from Coulomb's universal law, it acts along the line joining the two charges, assuming this also as a point charge, which is producing the Q also as a point charge. Only for sake of convenience, I have drawn it as a big charge. So any charge can produce a field, point charge or a big charge. So exactly joining the 2 point charges on the line, the force is present. Repulsive force means directed away from this charge, it's pushed away. So this force here will be less if the distance r is more. So if if the unit positive charge is brought close here, close to this charge, in this electric field, close to this charge, force will be more. So the field here is said to be more stronger. But if we consider a point far away in the same electric field produced by the parent charge here Q, far away the unit positive charge experience a weak force, a less force. It means the field here produced by this charge is said to be weak. So strength of the field or intensity of the field is less. So close to a charge, the field is stronger because it experiences the charge is able to apply more force on the neighboring charges. But far away, the field is said to be weak because the charge is able to, in the field, the charge is, or the test charge is experiencing less force, or the parent charge is applying less force. So closer to a charge, the field is stronger. Far away from the charge, the field is weaker. So how we are saying that field is strong? Because the test charge, if it experiences more force in the electric field, then the field is more stronger. That is, strength of the field is more. But if the positive test charge is experiencing, or any charge is experiencing less force, like when the test charge is placed far away, the field is less stronger. So we can know whether the field is more or less just by knowing whether the force experienced by a test charge is more or less. So due to this reason, the strength of the electric field at any point, it is defined exactly in terms of the force experienced by a test charge in that electric field. If the force experienced by test charge in the electric field is more, strength of the electric field is more. If the force experience is less, strength of the electric field is less. So for convenience, this test charge is taken as a unit charge or unit positive charge. Important thing is everything in electricity is defined using positive charges. Is defined using positive charges. So this test charge is compulsorily taken as a positive test charge or a unit positive test charge. So now considering, so why it is everything, every quantity in electricity is defined in terms of positive charges. The reason is for simplicity. Once positive test charge, what is happening to the positive test charge is understood. Negative test charge, it will be, if we take a negative charge instead of positive test charge, if the test charge is taken as a negative charge. Now here we can just see that it's a repulsive force. Supposing we put a negative charge here, it will be exactly opposite, it will be attractive. So it will not difficult to understand the behavior of a negative charge also, once the behavior of a positive charge is understood, or the situation of a positive charge is understood. Negative charge, it will be exactly opposite as we can see here. But for convenience, for simplicity, for uniformity, everything is defined in terms of positive charges. Negative charges situation can be understood very easily once the behavior or situation of a positive charge is understood. So now considering only a unit positive charge now. So the force experienced by or force acting on a unit positive charge at any point is simply defined as the strength of the electric field. So if the force experienced by unit positive charge is more, the strength of the electric field is said to be more. That happens only points very close to the parent charge which is producing this particular electric. We are now discussing electric field. So electric field always has to be produced by some parent charge. So in general, what is happening is, so whatever things we are seeing here are simple.